Hi, my name is Ladin Kotalavala. This is a PSCAD webinar on transient recovery voltage study. So this is roughly around 1 hour webinar. First 20 to 25 minutes, we go through a simple presentation on TRV. And next 20 to 25 minutes, we spend with the playing with some PSCAD examples and some scenarios for TRV. And last 15 minutes we allocated for questions and answer session. So you can type your question in the chat box in the webinar page. So I think we're good to go. What is TRV? Basically, TRV is the voltage difference observed between the breaker terminals immediately after the current interruption of the breaker. For example, if you have two electrical systems, system 1 and 2, connected with the circuit breaker, you know that as soon as you open the breaker, the system topology has been changed. So both the system 1 and system 2 trying to adjust for the new conditions, so there will be a transient movement. So the system 1 side, you see that transient voltage at U1 and system 2 side U2. So the difference of these two voltages you see as the TRV across the breaker. So the voltage across the breaker you see have two successive stages. The first stage we say is transient recovery voltage, whereas obviously you see the high frequency oscillations, which is called transient, and the followed by another stage, which is called just recovery voltage, which is basically the power frequency oscillation. By the time recovery voltage or the transients has been damped out, so you just see the normal power frequency oscillation as you see in this waveform. So this is the transient region, as you see the TRV, and this area called recovery voltage. So the transient voltage, as you see here, is having its unique features. I mean, like it's very high frequency. It's having a very high frequency, and also it damped out very quickly. I mean, in this case, you see that this is a sample waveform, which is within say half a cycle. You see that the transient is damped out. Generally, the objective of any TRV investigation is to verify that the TRV, or the recovery voltage experienced by any breaker upon interruption, upon current interruption, is within its capabilities. So, for that purpose, we have to consider different credible scenarios in the power system, which will affect your TRV. And we have to do, I mean, investigation of these different how these different scenarios affect on your TRV, and based on this TRV, then we have to compare on those with your capabilities of the TRV, capability of the breaker, and if you see any violation, and then that's the point you have to consider about any mitigation method. The nature of the TRV is dependent on the nature of the circuit being interrupted. As long as, I mean, normally we know that these oscillatory voltage are resulted from the basically the AC oscillations in the circuit, or either the traveling waves close by the transmission line close to the breaker. So this is a typical waveform. We see that we are having high frequency TRV oscillations upon opening the breaker. So you see the breaker current, which is interrupted at 3 different times. At the meantime, you see the breaker TRV, basically the voltage across the breaker. Let's have a little bit understanding about the current interruption process. This is a very simple explanation on interruption of the current. Generally, once the trip signal comes to the breaker, it takes approximately 12 to 20 milliseconds for the contact to be fully opened. Even though the poles are moving each other physically, the current is still flowing until the next natural current zero comes. So in other words, I can say that an electric arc will form between the poles to facilitate the current flow through the breaker until next current zero. The nature of the arc is obviously is having very high temperature, and definitely this hot, very hot condition inside the breaker will weaken the dielectric properties of the material. And if upon current interruption, if you see the excessive voltage across the breaker, it would lead to have a restrike across the poles. Means that arc can be created again. So, sorry. Generally, as you see that the breaker is, in most of the cases, you open the breaker upon clearing a fault. If you want to clear a fault, you open the breaker, and you see here, in this sample waveform, we have fault. You see high current after the 3 cycles. We open the breaker, and you see the current goes zero. But as soon as current goes zero, you see the TRV, or the voltage across the breaker, having an oscillatory period, and then it goes to the normal power frequency voltage across the breaker. Let's go, a little bit investigate what are the important features of this kind of recovery voltage waveform. So, as you already mentioned, the recovery voltage is having a transient period and then power frequency recovery period. In the transient recovery period, you see that something called RRRV, which stands for rate of rise of recovery voltage, which is basically initial recovery voltage, the initial rate of rise of the recovery voltage. So one important parameter down the road, we will explain a bit more down the road, and we compare with the breaker capability is the RRV. The other important parameter is the peak TRV, which is again an important parameter. So basically measured in kilowatts, whereas the RRV is measured in kilowatts per microsecond. So these are the two basic parameters down the road we have to compare with the breaker capabilities. So next, we will talk about modeling considerations in PSCAD once you want to do an TRV study. As you know, the TRV is basically fast events in tens of kilohertz. So the impact is of this transient is very limited to the local area around the substation, and also the circuit component inside the substation has major impact on the TRV. The remote system, say 1 or 2 buses away, generally there's no impact on the overall TRV response, but generally it is a good idea to develop at least 1 bus away system, which is providing you the correct fault levels on your substation, going to be studied for the TRV study. And also the other point is we down the road we will talk about the short line faults. For that purpose too, I mean at least 1 bus away system should be modeled with the correct, representing correct fault levels in the substation. As I said earlier, I mean it's very important to have a station representation of station equipment, including the all the stray capacitances. This is a simple example for system representation. Here you see, I mean, my interest is the low voltage side, 69 kV side of a system. This is a 138 kV system, and my representation is just 1 bus away from my interest station. So as you see, I mean, at the boundaries I have put a Thevenin's equivalent, which will give me the correct short circuit level at the station of interest for the study. And as you see, I mean, basically your interest may be the low voltage side of the station or high voltage side of the station. So whatever the interest, we have to model in detail. For example, here my interest is not the high voltage side, that's why it's representing as a simple bus. My interest is the low voltage side. So this will be a detailed representation of the station. So this is a typical detailed station model. So this is schematic diagram. You see the transformer, and both sides of the transformer you are having the disconnect switches, and then breaker, disconnect switch, and some VDs, CDs, and you go to the bus bar and have a breaker, and maybe you are having the low voltage overhead line or feeder. So this is a detailed representation of the station. So this is the corresponding PSCAD representation. As you see, I mean, you have the transformer and the surge arrestor, disconnectors, switches, and breaker, as on. So besides the major components, you see here all there is carrying a lot of capacitors, which is a representation of the stray capacitance of each component. So we will discuss this detailed later, but you see, I mean, basically what you have to do when you represent the station equipment. So sometimes your station may be a little bit complicated, but it still may be important to model it, because depending on the operational restrictions, operational procedures, and the configuration itself, the current through a particular breaker can be different during a fault. So, for example, if you're connected only, breaker is connected to one part of the circuit, and the other bus is isolated, so maybe you're having a lower short circuit level, maybe you have, I mean, isolated bus bars, so your short circuit levels can go up and down depending on the configuration as well as operation procedures in the station. So you have to pay a little bit more attention on that to ensure that you are getting maximum credible short circuit current through a breaker for the TRV study. So that's why, I mean, probably you need the detailed representation of the station and placing the breakers correctly, and And meantime, you have to get some information on how normally the station is operated. Is there any restrictions or any operation procedures that you should be considered during this study? So here we see the two sample representations. Mostly these, sometimes these bus bars are identical. Sorry, the bays are identical, so you can represent, I mean, in the same modules. Though it's a bit complicated, the modeling point of view may not be that much big task. And this is a simple example to demonstrate to you the importance of the stray capacitances of the equipment. Earlier we talked about that in the previous slide, that there are a lot of stray capacitances we represent with the capacitive, with a simple capacitor. So this will demonstrate you the importance of the represented stray capacitor. For example, say this is a simple system. You're having a source, transmission line, breaker, and the transformer. So you want to open this breaker due to a fault on the other side of the transformer. So upon opening this breaker, you will see that the voltage at the source side, E1, should be almost like a steady. I mean, you won't see anything happening at that side, but see the other side, E2, which is the second plot here, which is having very high oscillations upon opening. Simply the oscillation between the reactance of the transformer and the stray capacitance of the transformer bushing. So then actually if you see the voltage across the breaker, basically E1 minus E2, the TRV, you see that oscillation. So therefore this is a very good example to demonstrate the importance of representing the stray capacitance with the correct values. So in this simple example is the LC oscillation. Between the stray capacitance and the transformer reactors will appear as the TRV. As I mentioned earlier, the TRV is mainly due to the oscillation of the transformer stray capacitance and the transformer reactance, which is basically E2, as you see here. The oscillation frequency is very simple calculation. Anybody can calculate and validate it. And one point you can learn from here is if you play with these values, you can play with the oscillation frequency, which is basically the rate of rise of TRV. Right? If you know that, if you're having very high frequency oscillation, the rate of rise at the initial stage will be very high. If you have a low frequency, it means the rate of rise of the TRV will be lower. So having, pay your attention on this simple equation, we learn that, by playing with the capacitances, in simple words, adding a capacitance to here, you can take the control over the oscillation frequency, basically again the initial TRV, or in other words, RRRV. This table shows them typical stray capacitance values. Sometimes it may not be easy to find these values. The best way possible to get those values is to ask from the equipment manufacturers. Sometimes they provide those values, not always, because they know the best about their components and the stray capacitance values. But other way, it may not be easy task. So IEEE standard will provide typical values for each voltage level for these different station components. But you see that most of these values are in the picofarad range, the state capacitances, except the transformer bushing, which is having a relatively higher value in nanofarad range. In case of the absence of the vendors or manufacturers information on the state capacitances, you can refer to the IEEE standard and deduce some values from there and use in your simulation. The next thing is the type of faults affecting the TRV. Normally, we know that most of the cases you open the breaker upon to clear a fault. So, depending on the type of the fault, the TRV you observed may be different. As far as a three-phase ungrounded fault, which is considered to be the severe case, you will get the highest TRV problem, TRV issue, but it may be a very unlikely scenario. But three-phase fault, basically, if you come to the line-to-ground faults, those are maybe very, very common faults. But a simulation point of view, if you show that a three-phase ungrounded fault is simulated, and then the resultant TRV waveform is well below the breaker capabilities, then I would say you don't want to worry about these kind of faults, because this is a severe case. For the severe case, if your breaker is okay, you don't want to worry about the other type of fault. So therefore, some consultant would like to simulate three-phase ungrounded fault, and some people still do the simple way, most common fault type, line-to-ground fault. Another important point is the first fault to clear factor in TRV simulations. In other words, I mean, the first fault to clear typically has the burst TRV. You know that, I mean, the faults are open at 3 different times, depending on where actual current zero happens. So this is the simple example to demonstrate you the impact of the impact on the first fault to clear, depending on the system grounding condition. If the system is solidly grounded, neutral point is solidly grounded, you see that the voltage, the TRV voltage, which is given by the green color here, grounded system, you see the transient TRV voltage you observe upon opening this breaker. The blue color line is the voltage across the breaker when the system is ungrounded. You see that elevated TRV problem when the system is ungrounded. This is simply the in ungrounded system, upon opening this breaker, your neutral will be floated and your TRV will be superimposed with the whatever the effect coming from the neutral shifting. So these kind of things are already accounted in most of the standards, IEEE, IEC standards. So you don't want to worry about these things when you're doing the simulations, but it's a good point to know about these things. The next thing is the study scenarios we have to consider during the simulation. Sometimes due to the complicated nature of your station diagrams, you have to consider credible scenarios. For example, if all the breakers are closed, if you apply a fault at close to the breaker, which is called breaker terminal fault, so as long as everything is connected, you won't see any kind of transient or voltage across the breaker, but you have to ensure during the breaker opening, you isolated two systems, right? So this is something you have to be considered during the simulation. There are a few common scenarios we consider during the simulation. First one is the station fault. In other words, we call breaker terminal fault. It means we apply the fault at one terminal of the breaker and then open the breaker and measure the TRV. Other one is the short line fault. It means in our overhead transmission line on a cable, we apply a fault roughly around 1 to 3 kilometers from the breaker, and then we try to open the breaker and see the TRV. And the remote fault is a bit far away fault, can be a midline fault, mid span of the transmission line or cable. The other one is the fault on series compensated lines. Maybe another two scenarios is just opening a reactor or a transformer. There are several types of TRVs. One is the oscillatory TRVs. Basically, you see the TRV measured is having a nice sinusoidal waveform. This is resulted by the energy oscillation between the L and C elements. The other one is the triangular TRV, which is resulted by short line fault, which is having a traveling wave effect. As you see the E2, which is the short transmission line side, when you're having a fault, E2 side, which is the transmission line side, may have a traveling, due to the traveling wave effect, you may have a sawtooth or triangular shape of voltage. And when you embed it, see the difference, you will see this TRV, the triangular nature of the TRV. Then, once you get the TRV waveform, next thing is to compare with the breaker TRV capability. Generally, TRV capability curves are sometimes you can get from the breaker vendor. They do the testing on the breaker and they say this breaker is having capability of this much RRV value and this much peak TRV value. Or if it is not possible to have the vendor information on the breaker, probably you have to go to the IEEE or IEC standard, and they provide capability curves, so you have to compare with those. Generally, the capability curves are in discrete nature. They provide for 10% of the fault current. 10% of the breaker capability fault current, and then 30%, 60%, and 100%. So, for example, if the fault current through a breaker is 24 kiloampere and breaker is breaking that current and its capability is 40 kiloampere, then you have to actually take the ratio, and which is 60%, and you have to compare with the 60% curve. So we will talk and demonstrate about this in a second. So these are the typical TRV capability curves from IEEE standard. You have 2-parameter and 4-parameter curves. Normally, the voltage is below 100 kilovolt. There are 2-parameter capability curves. Above 100, there are 4-parameter capability curves. 2-parameter means you see that by defining the voltage here and the time in microseconds, you can define this curve or this envelope. But for this particular envelope, you need 2 points to define this, basically 4 parameters. and Y parameters. So basically, so you have to plot your TRV with this capability curves and see whether it's violating particular fault current percentage level. For example, the inner curve is 100% curve. Then you have the 60% curve, 30% curve, 30% curve, and last is 10% curve. So you see that, I mean, if the percentage of the fault current through the breaker is lower, you have more relaxed envelope, right? If you have 100% current, fault current through the breaker, you have a very restricted capability curve. So this is the breaker TRV envelope components we recently developed in PSCAD. I will show you this one in PSCAD soon. Now, I mean, basically you have to give your breaker opening signals to the component. It will draw all the TRVs and envelopes all together. You just have to go inside here and select whatever the voltage level you are investigating, and whether you want to go IEEE or IEC standard. So then they will be drawn together. So these are the few important points when you're selecting the different TRV capability curves. IEC standard provides capability curves for the breakers connected to the cables, overhead lines, for effective grounded system, non-effective grounded system, like that. I mean, they have different capability curves. You have to select based on your system. And this is finally the few typical results demonstrated here from some studies. So you see that, I mean, here we apply a breaker terminal fault. You see different waveforms, and this is the envelope. May not be that much clear, and you see the blue color curve is the TRV. You see that the TRV curve is, I mean, not crossing any of the envelopes. It means not violating. So no violations to any TRV envelope. And you see another example where you zoom in, you have, see here, it is violating 100 and 60% curves. Innermost is the 100 and then 60% curve. This is your TRV measurement, and these are the envelopes, right? But here is still not a violation, because it says during this particular simulation, the current interrupt by the breaker is less than 10%, or say 10% of the breaker capability. In that point, actually, you have to compare with the 10% curve, which is the outermost. It is not crossing. So even though you see that two curves are crossing here, but this particular application, there is no violation. These are the few study scenarios you have to consider about. I mean, some examples. When you're studying, maybe you're applying a terminal fault. Maybe you have a reactor close by, and with the reactor, without the reactor, and maybe you want to study a short line fault. These are some scenarios down the road we have to consider during your study. So that is we're done with the presentation. We can go to PSCAD. Some simulations we have set for the demonstration. So this is the, as I said earlier, this is the first demonstration for the first fault to clear factor. I mean, if you have a grounded system, you open the breaker. Let's see what you see on your TRV measurement across the breaker. We see the TRV peak value something around 200 kilovolts, and if you have an ungrounded system, in ungrounded system you will see with higher TRV. You see something like that, 500. So now we jump into actual TRV case. So this is a simple model. We developed for demonstration, but this is maybe 2 or 3 buses away model, but this is the station of interest. So you may not need this much big system, but just 1 bus away system may be sufficient. And once you go inside here, you will see that the detailed representation of your station having all the capacitance values. Importantly, this is opening a breaker, but due to a terminal fault. You see the fault is at one terminal or one end of the breaker. So this is a terminal fault. So this breaker, the other side of this breaker is connected to the transformer here. So transformer is having its own leakage reactance, and here I put 2000 picofarad or 2 nanofarad pushing capacitance, which you have definitely put there. So if you simulate this, and this is the breaker TRV component. So this is still not available in PSCAD master library, but if anybody is interested, but just sending an email to PSCAD support, you can get this component. Definitely it should be available in next release of PSCAD. So if you go inside here, you see that you can select TRV, IEEE, IEC. Both are now more or less same, and then different type of classes based on this one is basically for cables, S2 is overhead lines, then effectively a system. Normally high voltage systems are effectively earth, the non-effectively earth system, and then once you selected your system, then you go here and select the rated voltage of the system. Then basically you have to give the breaker status when you're opening the breaker and the TRV signal. And the right side you get the all the envelopes for the 3 phases and the actual TRVs. So right side I see this is my phase A envelopes and the actual TRV, phase B, phase C. So once I simulate this particular case, simply I'm having a TRV violations for all of my curves. Then it doesn't matter whatever the current I have broken. The breaker has been interrupted during this particular fault. So there's a big violation for all the curves. So in that point, we know that this oscillation is coming from basically from the transformer reactance and this pushing spray capacitance. So this oscillation. The mitigation. There are several mitigation options in this case. Some are really costly. One thing is you upgrade your breaker. Basically, then you have a much expanded set of envelopes, something like this. So you can see whether upgrading works or not, and you can take a higher braking capacity breaker. Basically, then your fault current percentage will be lower, or simply you play with, the system TRV. Basically, you apply some surge capacitor in the transformer, low side end here, and try to change this system TRV. So here, for example, I have put 20 nanofarad surge capacitor. This is very cost-effective solution in mitigation point of view. Once you put this 25 nanofarad surge capacitor, basically now it run, and now the transformer reactance is oscillate with the very comparatively large capacitance, which will definitely lower the initial rate of rise of the TRV. While it's running, I will have to mention about some other important few points. One is the simulation time step. As you know that you have to pick very high frequency oscillations. Probably your simulation time step be very small, like 1 microsecond or something like that. So it may take some time to run the simulation as long as the time step is so small. And the other important point is, you don't want to represent the system unnecessarily big. It will also give the time. So and now you see your rate of rise has been drastically dropped in the TRV waveform, and now only violating 100% curve. Right? This particular example, as far as I remember, the fault current is something like 30% of the breaker capability. You see that now there's no violation for 30% curve. Even there's no violation for 60% curve. For example, your breaker braking capability is 40 kiloamperes, right? So 60% means 24 kiloampere. You can interrupt up to more than 24 kiloampere fault current without any problem in this situation. Right? If it is something like 10-15 kiloamperes, you won't have any issue. So I think we're done with this simple demonstration on the terminal fault. The next and final demonstration is for a short line fault. Basically, the fault is happening around 3 kilometers of the feeder here. So then you are trying to open the feeder breaker here and measure the voltage across. So you see that in this situation too, you have a violation, and you see that this is the nature of little bit sawtooth type, which indicates that the dominating factor is the traveling wave from the transmission line side. So short line faults can create a significant effect on the initial TRV, as you see here, because of the very high frequency, the sawtooth type of voltage you observe from the transmission line side. So as you see here, this is a bit exaggerated sample. So you see, violation for all the waveforms, but in real life may not be. So, but here the main point is to demonstrate the sawtooth nature of the resultant TRV. So with this, I think we have demonstrated very simple two scenarios, terminal fault and short line TRV issue, and we just demonstrated one mitigation method for terminal fault TRV issue by adding a surge capacitor. So with this demonstration, I think this is time to stop the demonstration, and if you have any questions, you can write in the chat box in the webinar page, or you can just email us at support@pscad.com. Anybody is interested with the TRV envelope component, for the moment, unfortunately, you have to write us and ask from us the model until we put it into the master library with the next release of the PSCAD. So thank you everybody for listening to the webinar. So we go into the question and answer session now.